Hi, folks. Thanks to the organizers for inviting me, and thank you all for being here. It's quite early by networking conference standards, so I appreciate you being here. I want to talk about networks for machine learning. I want to talk about research for about 4 years in my group. And so one of the, turn this on. So it shouldn't be the strange news to this audience that machine learning is taking the world by storm. ChatGPT, fastest growing online application ever. In just 1 month, in January this year, ChatGPT had 600 million live inference queries from 100 million unique visitors. And do you know how long it took for Instagram, for instance, to have 100 million unique visitors? 2 years. ChatGPT did it in just 1 month. This is astonishing. Of course, disruption and innovations in search, content delivery, even coding. My argument is that machine learning has massive implications for systems and networks, and for us, the systems and networking community. I want to argue that we need to pay attention to 2 important metrics when we are building systems for machine learning. The first sort of metric is kind of obvious. We need to have our systems to have low latency. From training to inference, it appears that ChatGPT took 2 million GPU hours to train. What it means is that if you got 2 million GPUs, it takes 1 hour to train a ChatGPT model. But if you have 1 GPU, it will take 200 years to train. And so, I mean, OpenAI and all these companies have somewhere in between hundreds or thousands of GPUs. But that's not just the only picture. Latency for inference queries, if we were to include a ChatGPT query inside every Google search that we are performing, then the innovation and the interaction should be real time. And so every 100 millisecond added latency matters, directly affects the user experience. But I also want to talk about energy consumption. Traditionally, the way that systems and networking folks solve these type of latency or throughput problems is to throw money at the problem, add more and more resources, or design a lot of specialized solutions. What this means is that energy consumption is just going to be prohibitively large. ChatGPT's monthly electricity consumption is in the orders of millions of kilowatt hours. An average American home consumes about 3 orders of magnitude lower value, about 1,000 kilowatt hours. Putting training on the side, inference actually appears to be consuming a lot more energy too. Once you train a model, and then you need to serve a lot of inference queries, and very quickly, the energy consumption of inference is also going to be very, very large. And so my argument is that we need to build fast and energy-efficient ML systems. So let's take a step back. Let's talk about what is really today's the status of the way that we are serving machine learning workloads, training or inference. We tend to build data centers uniformly. We tend to have a simple or uniform congestion control protocol, say RDMA or DCQCN or DCTCP or TCP and whatnot. We tend to rely on a scheduling algorithm or a scheduling software to place jobs efficiently. We tend to have a same network topology called FAT3 or CLO network topology, or even end-host capabilities. And what I want to say is that today's data center networks are being bottlenecked for ML training and inference jobs. And throughout the talk, I'm going to show you evidence of why this is true and what can we do about it. But let me just show you folks one measurement that we took from Meta. So on the x-axis here, I'm increasing the number of GPU servers from 1 to 16. Okay? Think of a GPU server as a server that has, let's say, 8 GPUs in it. Kind of doesn't matter. We're interested in the network part, whatever that goes out of the GPU. So x-axis goes from 1 to 16, and y-axis is showing the network overhead. Think of this as the percentage of time during training that GPUs are sitting idle, waiting for the network to do its thing. Okay? So the higher the network overhead, the worse our efficiency is. And I'm showing 6 different DNNs, and so these are real measurements using the state-of-the-art parallelization strategy and the models that Meta is using. what this shows is by increasing the number of GPU servers, at the very beginning, there's no network overhead because it's just one server. But then look at this. At around 16 servers, the network overhead can reach to 60%. This is awful. This really means that these expensive GPUs are basically being wasted because the network is not doing what it's really supposed to do. I'm not showing you folks the name of the DNNs because we're just not supposed to tell you, but think of image recognition, language models, object tracking, and whatnot. Really, the name of the DNN doesn't matter. Different DNNs have different behaviors, and it kind of looks weird, but overall, the message is that the network is really becoming a bottleneck. So the high-level message that I want to bring across in this talk is that I want to talk to you folks about networking techniques to build high-performance ML-centric data centers. Okay? And the talk, I organized it across 3 key lessons. I want to talk about congestion control algorithms first, and I want to share with you folks kind of a bizarre and perhaps at the beginning surprising result that says fair congestion control algorithms, sort of the holy grail when we're designing a new congestion control algorithm or queuing discipline, it's actually not necessarily good for machine learning. The second lesson that I want to talk about is about reconfiguring the topology, literally the way that we're building data centers. And the third lesson, I want to talk about analog computing and the impact of data path engineering. Okay? So let me jump right into the first lesson. Here's the state of the art in congestion control mechanisms in today's data centers. We tend to use TCP or RDMA congestion control algorithms, okay? And then we tend to rely on DNN schedulers to place workers based on their topological proximity. And so here's in this picture, what I'm showing is a very, very simple data center. This is just a cartoon image. I have 12 servers. I have a DNN job that wants to be trained across 6 servers. This job requires 6 servers, okay? And so the scheduler is placing this job on 6 servers. And then suppose that another 6 servers arrive, and then the scheduler is also placing this training job across the other 6 servers. The scheduler did the best. The scheduler is optimal in this case. But server 4 needs to talk to server 5 because they need to exchange their gradients when they're training. And similarly, 8 needs to talk to 9 because they also need to exchange gradients. But just look at link node L1 in the middle. Obviously, there will be some form of congestion or contention between these 2 jobs. So even with ideal perfect scheduling, there are possible, especially in oversubscribed networks, the chances of congestion is non-zero, okay? So what we wanted to understand was what is the impact of congestion control algorithms when different ML training jobs are sharing a network link, okay? And to our surprise, what we found was fair congestion control algorithms are not necessarily beneficial for ML. Let me show you why. Let me set up the problem context, though. In this picture, what I'm showing you folks is 2 servers connected to a network switch with a link in the middle. And I'm setting the bandwidth of this link to be 50 gigabits per second. Okay, so these 2 servers are training the same ML model, and then they're exchanging parameters between. Okay, so let's look at the link utilization of this link in the middle. X-axis is time, and y-axis is the utilization of this link. Okay. For this particular training, I'm using a mechanism called data parallelism. So what happens is that at the very beginning, there's not much network traffic going on. This phase is usually the computation phase, especially the forward pass. And so these 2 GPUs are just computing the gradients according to their batch. Okay? But then immediately in the back propagation and all reduced phase, what happens is that the GPUs need to send the gradients to each other. Okay? So this is we call this a communication phase. Okay? Together, these 2 phases construct what is called the training iteration. And training goes on thousands and thousands of iterations. Each of these servers pick their own batch, compute the gradients until the model is converged to the target accuracy. Okay? And so this is sort of like the key point about DNN training. It's a little bit different than what we are used to the traditional, compared to the traditional data center traffic. traffic has a periodic sort of up-down pattern. Really, depending on the way that you are parallelizing the model or depending on the size of the model, this up-down may be different. It may not be kind of 0 and 50, maybe a little higher and lower, or the steps may be looking differently. But the point here is that there is this up-down pattern, and the pattern repeats itself. And actually, this pattern is also predictable. You can actually calculate the amount of traffic that is going to be exchanged, because we know everything about the model. We know how we're distributing it. So it's kind of cute, and then we end up leveraging sort of this pattern a lot. So now let me play with this setting. I'm going to add 2 more servers to the picture. I'm going to run another job between these 2 other servers. Okay? So I have 2 jobs sharing the link 50-50 in the first case. And we're going to look at the traffic pattern of this link in the middle. Okay? Well, in this case, I'm using RDMA congestion control algorithm, or TCP, doesn't really matter. They're both fair. And so what happens is that, for the sake of simplicity, assume these 2 jobs are both starting at the same time. The conclusions are the same if I just don't start them at the same time. But for just easier animation, just think about them. They both start at the same time. They're both in the compute phase, and then they're starting to send their parameters. So they're going to share the link 50-50. Okay? Now let me play with the setting. I'm going to modify this RDMA algorithm. I'm going to make one of the jobs more aggressive. In this case, I'm making green, job 1, a little bit more aggressive, so that it occupies 60% of the link when they are competing. When they're not competing, then whoever who's using the link is going to be able to get 100%. Okay? So if I look at the very first iteration, the traffic pattern of the first iteration, as you can see, green is taking 60% of the bandwidth. Right? So far, this is basically, I'm enforcing this setting. Okay? Now, think about what would happen if I run these 2 jobs, these 2 scenarios, for thousands of iterations. Who would finish the training faster? Intuitively, wouldn't you think that green is going to finish faster? Because I made green to be more aggressive. Whenever there's competition, green has to win. And intuitively, wouldn't you think that blue should be slower? Because I'm making it to be the slowest. Turns out, though, that if you run these jobs for thousands of iterations, blue and green are going to finish together, so their iteration time after thousands of iterations is the same, and faster than the fair case. Isn't that surprising? By making TCP a little bit unfair, I'm actually so-called accelerating DNN training.
Not surprising at all. Mike,
let me...
It's not surprising at all. You're anti-aliasing the thing and forcing them into different phases. Yeah.
Thank you. At the beginning... No, it's okay. Please, please. I'm setting it up this way.
Yeah, so this is not surprising. You're forcing it out of resonance, because
exactly.
When resonance went, this is not surprising at all. This is exactly what you would expect the system to do.
Yeah, in the beginning, we weren't that smart. So at the very beginning, when my students showed this to me, I was like, there has to be some mistake. Green has to always win. But then, as pointed out, I'm kicking them out of their sync. And so if I only am running everything with the complete perfect synchronization, these 2 jobs continue to compete with each other. But if I start a little bit of asynchronicity between these 2 jobs, what happens is that, of course, green for the very first iteration is running faster. But what that means is that green is going to start its next iteration also earlier as well. And so after a few iterations, what happens is that green and blue are going to sort of separate. They're going to interleave with each other. And so basically, this unfairness is a side effect that we are creating to sort of kick them out of their synchronicity, so that we call this interleaving between compute and communication of different jobs. Yes?
Do you think the resonance is a real-world problem? I mean, in a real environment, wouldn't there always be something that takes them out of resonance anyhow?
Yeah, we tried this actually. My response to my student was, there's always noise in the system. The perfect picture that we are showing is almost never happening. What we did try was to let the noise in the system to kick in. And indeed, they go into this interleaved state and then back into the synchronized state. They sort of oscillate. And so what we were thinking was, is there a way for us to kind of maintain and stabilize this interleaved state? How do we sort of get there? Okay. Of course, please.
So you said this was done with RDMA.
That's right.
So for better or worse, TCP Cubic actually will do this by default because it's highly aggressive. So the first guy will go for 100% of the bandwidth, and the other one won't get in until the first person is reduced and given some.
We tried.
And it turns out that you'll get this kind of oscillation effect, which many people consider bad. And I never really realized that it was, from an overall system point of view, a good thing.
Let's talk about this after the talk. We tried. I think the key point here is fairness or unfairness or oscillation at what time granularities. If you look at the bottom graph, it is also fair. If you look at these. So cubic, timely, DC TCP, DC QCN, we tried all sorts of congestion control algorithms, and they try to achieve fairness at a finer time granularity.
Yeah, that's true.
So that's the effect. Like, the RTT here is very, very small. And so what I'm trying to advocate for is not necessarily unfairness. I'm actually advocating for thinking about fairness in a different time granularity than instantaneous round-trip time fairness.
So I just wanted to add one comment, Manya. So yes, and I think the reality is that all of those other fairness and bandwidth allocation exercises were done in the context of VMs and SLAs.
Yeah.
Right? This is a different metric.
Exactly.
The metric is not, fairness is not a metric. Time to completion is the metric, and that's where the other results do not line up.
Exactly, yeah. Isn't this amazing? We have to think about the way our goal for congestion control algorithm is, because the workload is demanding a different success metric, like time to completion. Please.
So in the second case, the jobs basically counter-synchronized, let's say.
Yeah.
That's why in the later time, they just run at the full bandwidth, right?
That's right, counter-synchronize.
Okay, so this works in the trivial case of 2. What happens if you try to use more? Does this then disorder so you're dealing with a strange attractor type of thing in physics terminology here, right? So this could work for 2, but then may fall apart for many.
Thank you so much for asking that question. This is a perfect setup for me to move on. So can we just make this happen, magically go home and be happy? The world is not that kind. It's just more complicated. Turns out that we tried many different configuration of jobs, 2 or 3 or more. And in this table, what I'm showing you folks is we make the top job more aggressive, and what we are interested in is adding this little bit of unfairness should accelerate both jobs, not just the more aggressive one. And as you can see, sometimes it helps, unfairness helps, sometimes it doesn't help. Let's call it asynchronization. Sometimes this asynchronization helps, but sometimes it doesn't help. And so we started defining this thing called compatibility. Some jobs are compatible, some jobs are not compatible. And so the question is, well, how do we even identify which jobs can interleave and which jobs are just inherently, they're not clickable? Think of pieces of a jigsaw puzzle. The pieces have to be clickable, otherwise the gains are going to be more limited. So the question is, how do I find compatible jobs? Think about the time, like the x-axis time and the y-axis utilization. That's our jigsaw puzzle. And when we want to interleave different jobs, this is slightly challenging to think through. And so what we did was that we came up with a concept called geometric abstraction. Let's look back at the traffic pattern of one of those links at the very beginning of the talk. Now, let me pretend that the x-axis here is a string. It's a thread, it's a string. I'm going to rotate this string around itself. Basically, this circle in the middle, think of this as the perimeter of this circle is equivalent to one iteration. Now, because, remember, this job is repeating, it's periodic. So I'm drawing the same traffic pattern around this circle. And because it's periodic, all of these communication phases are going to line up around the same arc of this network, of this circle. Now, let me just even make it simplified a little bit more, too. Let me just color this arc as blue and say this colored arc indicates the region when there is some form of communication. I can make it more complicated later, but let's just think about this colored arc. Okay. Now, what am I going to do? I'm going to draw this geometric circle for all of my jobs. Let's say I have 2 jobs. These are 2 recommendation models. I drew the circles for both of them. And then I'm going to put these 2 arcs, put these 2 circles on top of each other and rotate. If I'm able to rotate, it's kind of the same as trying to see if the jigsaw puzzle, if I can make the interleaving happen or not. In this particular case, the communication and computations are such that they're sort of perfect match with each other. And so by rotating these 2 circles, the colored arcs are not overlapping with each other. But let me show you a case when, oh yes, John, please.
But don't those circles correspond to different iteration times, and so you can't overlay them because they're going to be constantly shifting in and out of phase with each other?
Okay, so these circles are determined based on when each job is running in isolation. When the job is running in isolation, the iteration time tends to be the same. So I'm not colliding them yet.
So you're assuming the job is always the jobs are identical in their computation and communication patterns. You don't have 2 different jobs with, for example, where the iteration time is twice as long as one as the other.
Oh, no, we do allow for that. I'll show you in the one slide after this. We allow. I mean, let me show you this one. In this case, they're also identical, but I'll show you an example when they're not identical. In this case here at the bottom, what I'm showing you folks is a case when the communication phase is very long and the compute phase is short. And so these 2 jobs are just not perfectly clickable, interleavable with each other. And so, I mean, the geometric circle shows the same thing. I can put them on the geometric circle. I can start rotating them, but there's no way for me to rotate these 2 circles such that the colored arcs are not overlapping. But let me go to John's question. So what if they're jobs with different iteration times? Oftentimes, we're going to have jobs with different communication patterns and iteration times. And here I have 2 little examples. There's job 1 with a 40 millisecond iteration time, job 2 with 60 milliseconds. These circles are different sizes. I can't really rotate them on top of each other. What we do is that we come up with a unifying circle, like a bigger circle, that has the least common, the perimeter is the least common multiple of the iteration times of both of them. In this case, let's say that the unifying circle has a 120 perimeter. And so I'm drawing the first job on this circle, and so the communication pattern repeats 3 times. And I'm also drawing the second job on this circle, and the communication pattern happens twice. And then I put these circles on top of each other, and then I start rotating. And so in this case, it turns out that after rotating with 30 degrees, then the communication phases are not colliding with each other. Okay, so in real life, you probably are not drawing circles and whatnot. You're probably going to translate all of this into an optimization formulation. The beauty is that everything is really actually easily translatable into a formulation. So I'm just showing you folks one way of formulating this. I don't really expect folks to read this. What I want to tell you is the optimization formulation takes the jobs, takes the profiling of each job, and then it computes what we call the compatibility score, whether or not the jobs are compatible, and if they are, what is the best angle to rotate them such that the compatibility score is maximized. Okay. There was a question in the back. Yes, please.
Yeah, so I understand what you're doing. Is the typical mark space ratio of most of these jobs close to like 50%? Or are we talking about their bandwidth utilization would be like down at 10%? Because if it's 10%, this is an interesting problem for multiple, but but running 2 jobs on a network, it's good that you can do this, but I would say that that's like trivial science. I mean, it's sort of relatively obvious and will sort itself out. But if you're trying to run 10 or more jobs over a common shared network, if the ratio of mark to space is not good enough, you're always going to fall into this failure mode. So it's not going to work to try to synchronize things this way, if that makes any sense.
Yes, yes. So we are observing gains for models that are, for multiple models that are sharing the network, for models that are various different communication compute patterns. And so my students and I are thinking about how to characterize it. I would hesitate to say that this only works when it's 50-50, or it's always going to work when it's, let's say, 10%. I think it's an ongoing research in a way of thinking about, in the model zoo, in the whole world of different models, there are many, many models that are in fact compatible. We recently have been looking into GPT models and language models, and we actually see bigger gains for those models. Happy to talk offline to see if we can identify. I think the problem of identifying mathematically or formulating a way of when this is useful is still sort of an open problem. We are mostly observing and experimenting with this setup. So I want to say 2 more things about this, and I'm going to move to the next topic. There are other ways of achieving what I just talked about. One is to time shift. Instead of middling and fiddling with the congestion control algorithm, I can just easily have a centralized scheduler or centralized controller that shifts the start time of different jobs. Like I was saying earlier, this is not really about making anything unfair. It's about enabling this interleaving. And so we have an upcoming paper that talks about using this property inside of a centralized scheduler that computes the start time of different jobs such that they start in a compatible way. Okay? There's one more way to do this. What I've been thinking about with my student, this is ongoing work, is there a congestion control algorithm that can automatically stabilize to this interleaved state? In the earlier examples, we were forcing, say, 60-40. What if there is a queuing discipline that automatically, without anybody telling, 60-40 or who should be 60, who should be 40, can it actually automatically converge? This is actually a recent result that my student just produced, to be honest, last night. And so what he shows is, by changing the aggressiveness of the TCP algorithm, we're able to automatically, after a couple of iterations, to kick this synchronization. And so we have an algorithm called MLTCP, and we're looking actually for partners from Netdev community to help us push this upstream. So find me after the talk if you're interested in this, or email me. Okay, so let me move on. Now I want to talk about reconfiguring the network topology. So question that I want to ask is, I talked a lot about congestion control and sharing. Is it possible to avoid sharing entirely if I were to have a dedicated piece of the network topology entirely for one single job? Is there value in that at all? And when I say change the network topology, I literally mean change the wiring. In this picture, these are, like, say, 3 topologies with the same wiring. What I mean when I say reconfigure is literally change the links, the way that these servers and these computers are connected with each other. Kind of like wireless, but except that in this case, we're talking about actual physical links. Okay. So let's look at why do we want to even do this, and what are the possible gains. Here in this example, in this slide, I'm showing you folks a traffic pattern measured from also Meta's data centers on the amount of traffic that different DNNs are sending to, different servers are sending to each other when we are training different DNN models. So on the x-axis I have, or on every single plot is a different model, and then the heat map is showing the amount of traffic. Intensity means the amount of traffic. So like the darker the square means more traffic is being exchanged between the servers. Okay? And so if you squint your eyes, you could kind of almost see a diagonal pattern on each of these heat maps, but there's also a lot of other types of traffic that's happening too. I'm not showing you folks the exact amount on the color guidelines, but because we're not allowed to share the exact value, but think of it as several gigabytes. In the coming slides, I will show you one example that we ran. Okay, so the lesson we learned was kind of before, the traffic pattern for one job is repeatable. So it's predictable, iteration after iteration, if I'm looking at each of these jobs. But then across different jobs, the traffic pattern is different. It's not actually that surprising to think about this, right? Different models, different size, different number of servers, parallelization strategy is different. So of course, we shouldn't really expect everybody to be having the same traffic pattern. But look at this heat map. The heat map is not always dark or always sort of light. There are pieces of the heat map that are brighter, and there are pieces of the heat map that are sort of lighter. Okay. What this means is that this type of traffic pattern is actually match made in heaven with optical interconnects. Think of an optical interconnect as a reconfigurable interconnect, the topology thing that I was changing. Why, first of all, building a full bisection bandwidth cluster is basically a waste of money, because not the entire heat map was not always dark. So there are parts of the heat map that are not dark, and so you're wasting your bandwidth if you're providing full bisection between all of the servers. And this traffic pattern is predictable. For over 10 years, we've been trying to come up with optical interconnects and reconfigurable interconnects, lots and lots of research papers. But only very recently, companies like Google are announcing that they're actually using optical switches in their ML training clusters. Why? Mostly because ML traffic is predictable. Coming up with a control algorithm that looks at the current traffic matrix and then adjusts the topology accordingly is very challenging. It's very hard to do this in real time for conventional data center traffic. But the beauty of ML is you don't have to do this. You can actually come up with the topology before even running the workload. This is what basically we do. And a couple of years ago, we proposed this concept of one-shot reconfiguration. One-shot means come up with the topology now, change the topology, and let it be. Let the whole training run for a day or 2 days and whatnot. It's actually better than keep reconfiguring and trying to guess what to do next. And it's also better than not doing anything or having a totally static topology. So practically, how do you even do this? There are many, many ways of building these type of reconfigurable topologies. I'm just going to show you folks one way. It's not the only way. The concept is that you would have servers, or think of this as racks of servers, doesn't really matter. You have some unit of communication at the bottom at the sort of a first layer. And then you have a new series of optical switches at the top layer. Okay? These optical switches basically provide the reconfigurability. The way I think about optical switches is a bunch of mirrors. They're just mirrors pointing to each other. And then reconfiguring an optical switch involves changing the orientation of these mirrors. And traffic is in the form of light. So these mirrors, by reconfiguring the mirrors, you're literally saying traffic goes to this port or the next port and whatnot. Okay? So for instance, you can interconnect two ports. You can change the orientation of the mirrors to say these two servers communicate with each other or another sets of servers communicate with each other. The difference is that these are circuits. It's kind of like when you pick up the telephone and you're connected to somebody, unlike electrical switches when it's packet-based. One sort of key aspect here to remember is this concept of interface or degree. So here I'm drawing you folks this, degree D interfaces. What I mean here is that each server is able to connect directly with a certain limited number of other servers. Think of this as the number of NICs, network interface cards, on each server. Maybe it's 10, maybe it's 12, maybe it's 2 even. But that's sort of that's sort of the budget that we have. Think of this problem as kind of like a graph problem now. You have a bunch of nodes. We want to create a topology, a graph. And the budget is this number of neighbors that each node can have. Okay, we'll come back to this budget in a couple of slides. So why is this hard? Why don't people already do this? Turns out that this whole space of what is the best parallelization strategy, what is the best network topology or communication collective, it's just hard. This is a very vast search space, many, many, many different settings. Suppose that the optimal point is somewhere here, star. Okay, this is a very conceptual way of telling you why this is hard. What we do today is that we fix the network topology. And so we just basically, for a given network topology, we find the best parallelization strategy. And of course, there's a possibility of missing the optimal point, right? If you're only moving in one plane and then going into and optimizing the second dimension. What we are proposing is a slight modification to this. What we say is, let's fix the topology, find the best parallelization strategy, but then let's not give up. Let's go back and fix the parallelization strategy and look for a topology. Then let's go back and fix the topology, look for a parallelization strategy, and so on and so forth. Let's try to see if we can walk this huge search space and see, hopefully we can land into a better position. And so this technique is kind of common technique. It's called alternating optimization. And so we propose the work called topo-opt, where we are optimizing the parallelization strategy, and then we fix the parallelization strategy, we change the topology or optimize the topology, and then we feed the topology back to the parallelization strategy optimization, and then we just sort of repeat this hopefully righteous cycle. And at some point after we are not really moving forward, we end the problem, and then we say, here's the parallelization strategy and the topology together that I found. So let me just talk a little bit about how do you even find this topology? At the beginning, it felt like, OK, this is easy. We're networking people, so if you have a traffic matrix, just find a good topology for it. Turns out that, remember the degree thing that I told you? Because of this degree thing, it's not that easy. So let me show you one example. This model here on this picture, on this slide, is a deep learning recommendation model. You know, when you open your Facebook page or TikTok, or I don't have a TikTok account, but for those of you who have a TikTok account, when you open your TikTok page or YouTube, and you see all these recommended content, companies are using this deep learning recommendation model. Okay? And this sort of challenge or the beauty of this model is that it has this thing called embedding table, this green stuff. Embedding table, think of it as a giant, it's not a database, but you can think of it as a giant database with a lot of values in them. And so Facebook collects so much data from all of us. And so the model sort of inherently has this knowledge of so many users. And so these embedding tables are so large, they don't fit the memory of one GPU. And so if you want to train this model, you can't just copy this model in one GPU. We have to separate these embedding tables and put them into different GPUs. And so what I'm showing you folks here on the right-hand side are 16 servers, 16 nodes that I'm distributing this model across. Okay? And because I told you these embedding tables are large, I have to distribute them across different nodes. In this case, 0, 3, 8, and 13. Suppose that I have 4 embedding tables. And so I'm putting these 4 embedding tables. This is a random decision, but any of these 4 nodes, okay? The rest of the model, the blue part, the part that kind of looks like a Pac-Man, the blue part is very computational heavy. So it's to my advantage to copy this across all of my nodes. And so that's why you see the blue part on all of these servers, and then the green parts on just some of the servers. This technique is very common. This is basically the best practice in industry. It's called hybrid data and model parallelism. Okay? The model parallelism part is from these embedding tables, because I'm actually parallelizing the model as well. Okay? And the data parallelism part is coming from this blue section. Okay? So okay, this is the best practice, doesn't matter. NVIDIA and Meta and other companies are doing this. Why do we care? Let's look at the traffic pattern coming from this parallelization strategy. Okay. Here's the traffic pattern. It kind of looks like what we had from the measurements before. It's cleaner a little bit. Okay. So what we're seeing is this diagonal blue line and these vertical and horizontal green lines. Okay. This diagonal blue line is coming from the blue Pac-Man part. It corresponds to this all-reduced traffic pattern. All-reduced means all of these servers, all of these GPUs, have to send their gradients to each other, and then they have to take the average. Okay? At every iteration, this has to happen. Otherwise, they're overtrained to their local data. And these green vertical and horizontal lines are because of those embedding tables. Because all of the nodes now have to talk to these other nodes, and vice versa. Okay? And in this case, because we are training this model, I can show you folks the maximum amount is 4 gigabytes. This is actually a tiny model, but already generates 4 gigabytes of data for the network. This 4 gigabyte can be arbitrarily large as well. So, okay, so we got this traffic pattern. We want to build a topology for it. Okay? We should be able to do this, right? Ideally, look at the traffic pattern, generate a topology. Easy peasy. The problem was that degree thing. I cannot always match the traffic pattern. Okay? If I had so many degrees, then yes, I would have matched. Like, think about these horizontal and vertical lines. It means that one node has to be connected to every single node. It's really hard, right? If your cluster has 30,000 GPUs, you don't have 30,000 NICs, or even 128 NICs. Our number of NICs are usually, say, 12 or maybe a little bit more. Okay, so what should I do? Again, many reasonable options are available. Think about looking at the traffic matrix, looking at the largest values, and sort of building something that's optimized for the largest. Right? This is a very reasonable heuristic that we tend to do in networking. Let me just make some assumptions here. Assume that the number of NICs is 3, and everything is unidirectional. So each node can send and receive from 3 neighbors. If you look at the largest blue, and your budget is 3, what would you do? Match blue, right? Match entirely blue. And blue says what? 0 to 1, 1 to 2, 2 to 3, etc. My budget is 3, so the best thing I can do is to have 3 sort of rings, a really fat ring here. That's pretty good for blue, right? The highest amount of bandwidth that I can to transfer these 4 gigabytes. But I mean, I didn't really do a good job for green. A green flow has to travel. I mean, ring is not really great for hop count, basically. Okay, so scratch this idea. Let me do something that's really good as a network diameter. Let me come up with a topology that's really good for that. Expander graphs, or even random graphs, have really good diameter properties. And so suppose that this is a random graph that I come up with. And in this case, this is pretty good for green because of a 1-hop diameter. But I wasn't able to give too much bandwidth to blue. Right? I'm only available 1 NIC for this really heavy blue traffic. So again, I didn't do a really good job. It's sort of like 2 competing goals. You got the big blue, and then you also have these green stuff that need low diameter. So I need high bandwidth for blue and low diameter for green. So what would you do? The key lesson we learned is so interesting. It was kind of mind-blowing to me. The traffic matrix is not God-given. You can change the traffic matrix. Why? Because we're talking about all reduced. We're just averaging people. In averaging, order really doesn't matter. 1 to 2, 2 to 3, etc., versus 1 to 5, 5 to 10, 10 to 15. So I'm going to show you another perfect all-reduced sort of traffic pattern, where instead of 0 to 1, 0 is tending to 5, 5 to 10, 10 to 15, and so on and so forth. Think of mathematically averaging, ordering order of entries in an averaging mechanism doesn't matter in an averaging formulation. So I'm going to create, actually, there are many, many, many different ways, different orders. Think about it, like, 1 to n, you want to average these numbers. Several different, many n factorial different ways of averaging. And each of them are going to result in a different traffic matrix. We call this mutating the traffic matrix. Well, what am I going to do with this? I'm going to put all of them together then, later. So by putting all of these together, I'm sort of averaging out the entire traffic. It's sort of like a load balancing trick now. And see, my traffic pattern is no longer that dark blue diagonal anymore. My traffic pattern is kind of tamed a little bit more. I have more green and light blue. And so I have good diameter because I'm no longer just a ring of 0 to 1, etc. But I'm also, because the way that I've constructed this, I'm also giving high bandwidth to my blue all-reduced traffic. So we also show that this algorithm actually bounds the diameter of the topology depending on the number of nodes that you have and the degree of the servers. Let me tell you one quick note about how we come up with this. Here I'm showing you all sorts of different weird things of ordering in that average. These are all valid orders. Some of them look a little bit weird and some of them don't. There are many, many of them. There are actually n factorial different permutations. To make the problem space more tractable, what we do is that we separate the regular ones from irregular ones. We don't know actually what to do with the irregular ones, so we kind of throw them out. And then we only use the regular permutations. And then by just using these regular permutations, we reduce the search space to be O(n), where n is the number of servers that we have. And we show that this technique works for non-ring or reduce, let's say tree or reduce algorithms too. Okay. We implemented this code in this sort of regular permutations in nickel, and we have a little prototype with NVIDIA GPUs. I want to show you folks a quick video of the setup we have. So remember I told you the optical switch is a bunch of mirrors? We didn't have that at the time that we were doing this research. So we literally used a robot that takes the fiber, moves it up, and then puts it back into another location. Think of it as a programmable patch panel. Let me see if the video plays. Yeah, so this is the arm of the robot. You see it's coming up with the tip of a fiber. It's going to move, and then it's going down and then placing this fiber into its new location. And like this, you can just actually reconfigure the topology. This is actually a startup that I'm advising, and they're literally like building these what they call reconfigurable robotic patch panels. Fun, eh? Okay, so their simulation results really doesn't matter. What we show is that compared to cost equivalent FAT3 clusters, we are accelerating DNN training by a factor of 3. Hopefully I convinced you folks that the topology here matters, and you can reconfigure the topology to get better training time. Okay. I want to have one slide talking about what does this mean for the Netdev community, though. As I was telling you folks, companies like Google are now also announcing that they're using this type of topologies for their DNN training. These are called sort of direct connect topologies, when you no longer have these electrical switches all the way in the middle. Okay? And this end host networking stack is critical for these type of topologies. So routing, load balancing, communication collective, all of that has to happen at the end host server. And I think Netdev community is really in a critical spot to help us optimize this sort of direct connect topologies for DNN training. Now let me move on to the third lesson. I want to take a few minutes and talk about a concept called analog computing. So what is photonic computing? What is analog computing? The concept that I want to talk about is to use light waves to perform computation entirely in analog domain. So no more transistors, basically. Or no more transistors for certain types of computation. Well, computers were born analog in the beginning. Charles Babbage did conceptualize computers in the 1800s as analog devices. And then using optical computing for AI acceleration is a popular topic. It's not new. I didn't invent it. It's been around since the 1980s. Why are we even interested in talking about this? What's the gain here? The optical devices can perform computation super fast. Turns out that their clock frequency is really, really high, hundreds of gigahertz, compared to a clock frequency of a GPU or a TPU, roughly around 1 gigahertz. Okay? Energy consumption is also quite favorable. But even since the 1800s and whatnot, we haven't really had practical traction of these photonic computing or analog computing. They're always in science and nature papers, but it's really hard to build them for real. So that was basically the question that we were interested in about 2 years ago. We wanted to really understand, what does it mean to build a system? Is there anything that us as the networking community can do to help lift up this technology, or no? So I want to show you just a concept of what is it that, why am I saying computing can happen in analog domain? This little device here is called the transceiver. It's basically a very commodity device in data centers. We use it in basically every data center to convert digital data to optical fiber, into the optical fiber, and then we transmit data into fiber to the other host. Right? This thing is super cheap. It's like about, I think this one is about $30 from a company, and then you can just basically have it shipped overnight. It's that sort of ubiquitous. It's basically communication. We're not entering compute land yet. My students sort of broke this thing up to look into what's inside. And so there's sort of two components here. The top here is the digital part, and the bottom here is the optical part. The digital part is where the digital data enters this device, this transceiver. And then there's a laser and a modulator. Okay? So the laser is just creating constant waveguide. For those of you with EE background, this should be a no-brainer. The job of the modulator is to basically modulate light onto this constant carrier light. Right? And so the modulator is going to modulate basically light. In this case, I'm showing you folks amplitude modulation, which means that the amplitude, the intensity of light is changing based on this analog. So now let me move here. So now here's the trick. Let's put a second modulator. Okay? Now, the second modulator is also going to modulate light based on the incoming electrical data. And like we said, the process of modulation is to modulate based on the carrier light. But now this is the second modulated light is the carrier. So the output of this modulator is basically this light, the second modulated light, modulated based on the input here. Inherently, if you write the Fourier transform, this means multiplication. And so you can put a photodetector to collect this light, kind of like a solar panel battery. Or you can just read all of these results. Okay? So look, what did I do? I performed vector multiplication without any transistors. Right? This has been shown in many, many science and nature papers. I didn't invent this part. So the commodity modulator that I showed you folks, you can buy it for $30, can run at 15 gigahertz. You know why? It's basically material that reacts to light. It literally doesn't have a clock signal. The thing is lithium niobate, the material. It just reacts, and the way it reacts is fast. Okay, great. But this modulator reacts to anything, basically. It just multiplies air by air all the time. It doesn't have instruction set to say multiply now or read now. It's not like an ALU that we are sort of used to. So that's why this thing is hard. Working and embedding this into our devices is hard. I'm going to show you folks one example. So here's a very simple DNN model. What it does is that it recognizes handwritten numbers. Like here, I'm inputting number 6, and then I'm reading value 6 out of this. But even such a simple DNN model has many, many operations. And so let's call this, a series of operations. Some of these operations can be done in the optical domain. Some of these operations cannot be done. Let me give you an example. Negative numbers. Really hard to represent a negative number with intensity of light. Right? Even zeros are hard, but let's talk about negative numbers. So I have to do some stuff in digital domain and some stuff in the photonic analog domain. So I need a control logic. This is where Netdev and this type of engineering sort of becomes very important. I need to be able to build this control logic so that it doesn't sort of block this fast data path, okay? What happens today is that the control logic is deeply coupled. And so packet arrives, there's some sort of packet processing, then the software talks to the sort of the control logic, flatten the packet, okay, multiply, accumulate. There's all this sort of communication going back and forth with the control logic. Okay, this is the part, this control logic is the part that we can optimize. And so it's almost like you got a Lamborghini, but you don't really know how to drive. So every time you take up the manual and it says change gear to 1, okay, and then take up the manual and it says give it a little bit of gas. And so that's how we tend to build these super fast optical systems, which we end up choking them, basically, because we just embedded this control logic is so embedded, and it's sort of like a simple Python program as the control logic. This type of work basically defeats the purpose of using fast compute. So data movement is incredibly important if you have a really fast compute primitive. Let me show you an example. This is how today's demonstration work. There is like this Python program running in a laptop using these expensive devices. The optical stuff, yes, it's been around and it's super fast. But then once you look at the end-to-end latency versus the just photonics latency, there's like 5 orders of magnitude difference. The photonic stuff is fast, but then the data path is not great. Same for energy. The photonic stuff is super energy efficient, but then all of these other devices need to consume power. So we really didn't save anything. So that's basically why this relates to us. We need to co-design these fast compute systems with the digital system. Here's one way of doing this. This is what we just published in the SIGCOMM conference in the summer. We came up with a programming abstraction for these photonic computing systems. We install our abstraction in the data path, and then we get rid of the control logic entirely. Again, kind of like how we drive, right? We learn driving, and then we just drive automatically with our muscle memory. That's sort of like the inspiration. We want to program the data path, and then we want to get the control logic out of the way and let the data to sort of zoom through. This control abstraction is actually should be simple, but should also be powerful. And here's our observation. There's an abstraction we call count action. What it means is count the number of multiplication. Say your DNN has 300 multiplications in the first layer. Once you're done with 300 multiplication, trigger the next action. Maybe it's a softmax or ReLU or nonlinearity and whatnot. Turns out such a simple abstraction, at least for the stuff that we've been trying, is good enough to enable us to program the data path. So we use this sort of count action abstraction to do challenging tasks like synchronizing data streams coming together. Putting everything together, we are proposing sort of like a smart NIC that has this photonic stuff somewhere in it, but then the innovation here is really on this data path of synchronizing and feeding data into the system such that we are not bottlenecking the fast photonic with the digital parts. We have a plug-and-play kit for developers who want to play around with this. The code is online, and we have sort of like an API, a Python API, that enables you to go in and then log into the system and then basically sort of like multiply numbers in the photonics domain. I want to show you folks one quick video of how we actually do this. So here's the setup before I show you folks the video. This is our test bed. We have modulators, photo detectors, and we have an FPGA here on the top left. This is basically where the data path, all of our implementations are inside of this FPGA. These modulators and photo detectors and the fancy stuff, you can just buy them online. These are very commodity devices. So in the video, I'm going to show you folks accuracy, and let me just give you a high-level takeaway. What we should do is to look at the accuracy. How accurately can I multiply numbers? Okay. And so in this picture, what we're doing is that pick a bunch of random numbers, multiply them in the digital domain, and then multiply them using this setup, and then plot them against each other. Ideally, if I'm accurate, I should have a diagonal line. Right? So I'm going to show you folks the video. Let me see if it plays. Okay. So here's the setup. We're just bringing up Linux kernel on our FPGA. So the system is up. It's called Lightning. We have a Jupyter notebook to help us access the API. In the beginning, we run some calibration. The reason for this calibration is, you know, when I show you, let's say, 0.8 light intensity, it's actually not exactly 0.8 volts. There's a relationship between 0.8 dB and 0.8 volts, for instance. So, but this relationship is constant. And years ago, Einstein came up with this sort of a photoelectric effect that this constant is calculatable. Depends on the parameters of the system. But we can just run calibration at the beginning and then calculate this constant. OK, so I'm going to multiply two numbers, 0.7 and 0.9. And my goal is to get 0.63. I'm going to multiply them in the photonic domain. So in the beginning, I'm just going to take 0.7. I'm going to represent it in the analog domain. OK, here's 0.7. Different lines are different experiments. This is so quick that I can just quickly run it multiple times, right? I'm saying 0.71. Good enough for machine learning. Let's look at it. OK? Now, let me show you 0.9. Here's 0.9 in analog domain. I'm reading it roughly 0.9. Again, the errors end up not really mattering that much. And then let me just multiply 0.7 by 0.9. And you see for the accuracy, for the precision that I was interested in, I actually do get 0.63, which is exactly what I wanted in the first place. And then here's what we're doing, is that we're sweeping a bunch of random numbers, multiplying them in the FPGA and multiplying them in the photonic domain, and then plotting them against each other. You see, this accuracy is 99.9. It's even better than what I had on the slides. OK. So kind of zooming up, final remarks, what I think is basically the message of my talk is that innovation in networking do come from applications. In this case, I've been trying to talk to you folks about ML. I do think that networking stack is vital to application performance in distributed settings. And I hope that I conveyed a few opportunities for the Netdev community to be involved with ML networking. I talked about, congestion control, topology optimization, data path engineering, but I don't think this is a comprehensive list. I think there are tons and tons of other opportunities for this community. In the end, I want to thank my students, collaborators, and mentors, and all of you for listening to my talk. Thank you so much. Happy to take questions.
Really spectacular talk. Thank you very much. There was one thing that makes me twitchy, which is about when you talked about having a topology that could take an average in any direction. And at the levels of precision that you're at, no, you're going to
overflow or underflow and have a different result depending on the random topology. So yes, you're agreeing with me. It makes me nervous to know I'm going to put numbers in and get a different number out depending on the topology. The second question is, are you fiddling with posits or posits any? Are you familiar with that floating point representation?
Yes.
It's one of my big hopes is in the community. Is anybody here familiar with IEEE floating point? Does anybody here trust it? So my big hope for seeing posits get more use in the world is they'll be able to cross-check a lot of simulations with something that works better. Anyway, thank you very much for a great preso.
Thank you. So on the order of averaging, I do agree when you're dealing with large numbers, at some point you're going to overflow, and the order does matter. What we've been trying to look into is to quantify how much this affects the accuracy. And so I think this is challenging and it's important. It tends to be, this is just experience. I'm learning that machine learning is quite forgiving to errors. I should be very careful making a blanket statement. Our so far experiments are showing with proper quantization and with proper scaling, our accuracy are not impacted. But this is just, this is not a blanket statement. On the POSIX question, huge fan of POSIX. I really wanted to be more involved. I really want folks to, I should be careful not making political statement, but Nickel is doing a really good job. And Linux and TCP stack needs to catch up. There's room. There's room to catch up. I'm a huge fan of making something with POSIX happen.
Hello. So I have two questions.
Oh,
yes. Yeah. First one is the geometrical representation of the communication between the DNNs. It looks like a transformation of time domain to frequency domain, right? Is there a reason not to use a Fourier?
We thought about it. We couldn't make it work. But maybe we weren't really thinking too deeply about this. But yeah, I agree. I don't have a good reason.
So the second question is there a reason not to design the network topology problem as a vehicle road problem?
As a what problem?
Vehicle roads problem.
What is vehicle route?
It's the problem of, it's a graph problem, right, of actually finding the best path for vehicles that are going to visit several
vehicles.
Vehicles.
Got it.
So the vehicle road problem. It's an NEP problem, right? But usually you can actually transform that to a simplex algorithm that you can run.
I see.
Yeah.
I see. Okay. Let me give some speculations of my understanding. Many ways of designing a topology. And so what we wanted to do is to merge this concept of your traffic pattern with the topology. So most of these, say, Dragonfly or different routing problems, maybe the vehicle routing is going to help with the communication collective. What is really the best communication collective? But once you have a traffic matrix coming up with the topology, what we found was that that path is not the best path. What we should do is to think about changing this traffic matrix and topology together. But I'd love to catch up with you after the talk to discuss this more. Thank you for suggesting.
So I actually had a continuation to the
Please.
question, right? So many of these things are, so you alluded to the fact that there's a collective pattern, all reduce is not all gather is not reduced or reduce scatter. The question that I'm wondering is how much of that parameter applies to many of these analyses, right? Because specifically, if I have a combination of reduce scatter with all reduce, the topology optimization is no longer a single parameter decision. You may have to find that in between you're reconfiguring and doing things that are kind of interesting and different.
Good question. So we are thinking about in between. At the beginning, it was hard. it's more challenging to do in between. You got to be smarter to choose when. But we are thinking about not just training, but also inference. But for training, forward and back prop. LLMs, there's different patterns in between.
Yeah, that's right. LLM, DLRM, the pattern becomes.
Yes.
Yeah.
Yes.
Okay. That's all I had. Oh, there's one more question, Tom? No.
Yeah, so when you were talking about the accuracy not being a big issue, are you talking very specifically about things like cosine analysis for phase space of vectors to try to figure out proximity and those types of things? Is that, because that's a huge area of interest and they don't need to get hyper accurate. They just want to know where some vector is in some n-dimensional space, how collinear they are, right? So that's a very useful thing in machine learning activities.
Got it. I wasn't thinking as sophisticated as you put it. So that's a really good way of thinking about it. What we've been doing was to literally run the training and introduce inaccuracies, basically, and then observe that the final accuracy of the model is within, if I remember correctly, 3%.
Well,
If you were
close enough for government work.
exactly. Thanks. Yes.
Yeah, I have a question because you shown that you tried to plug this solution of the like lightning path multiplication into the NIC, but the problem with the L1 of the NIC is that they use PAM4 and they use forward error correction, which means basically you will scramble over the FEC data there. So does it mean that you just designed a separate device or tried to use the like PAM4 and stuff like that?
Good question. So let me tell you. Here, all the PAM4 stuff happens already. So I go from optics to digital, optics for compute, and then back digital. I am thinking about what you're suggesting, to do compute already when I'm in optics. And then what would be the impact of PAM4? But at this point, the moment that I have data, it's already digital.
Yes, but what about FEC codes? Forward error?
Already error corrected and whatnot. So it's just numbers to my system.
Yeah, but they are like FEC is added on the layer 1, so you put the data that you want to send, and the file layer will calculate and add the FEC there.
The data is coming from a remote, like somebody typing a ChatGPT request. It turns into PAM4 and whatever. This here, this MAC, the CMAC module basically performs all of the error correction and whatnot, and it gives me a number.
Okay. So then you like convert it to light again and then do the calculation?
Later on, I do all of my fancy things, like prepare the data, line it up perfectly, make it parallelized, and then I feed it to these DACs, then it becomes analog, and then there's a laser here that again generates light.
Okay.
It's a little bit of a double work. I'm thinking about what you're thinking, but as you're kind of alluding to, it's not that easy.
Yeah.
Yeah, thanks.
Thanks.
Just coming back to congestion control, of course, it's been well known forever that fair sharing is the absolute worst possible scheduling algorithm. When you have large jobs, it all takes the same amount of time. Everybody finishes at the worst possible. Everybody finishes last, basically. And so the key idea seems to me is run to completion. That's the goal. You want to let somebody actually get to the point where they're finished and they can go on and get useful work done. And the priority mechanism introduced was a way of inducing run to completion. But it seems like there was really a means to an end of getting run to completion. And so I was wondering, there must be other ways also of getting run to completion in this world. And in particular, it seemed like the time constants are large enough. These phases are lasting, it looks like hundreds of milliseconds, that you could potentially centrally schedule that, because the applications know when they're about to go network bound. A central scheduler could say which application gets high priority, everybody else is low priority, and you could achieve then you could actually achieve sort of perfect run to completion behavior, no?
Yes, you're totally right. We are just coming up with one way of making this happen, but I think there are many ways. I think we should all think together. I welcome your thoughts, but totally on the spot.
Have you considered? Oh, sorry.
Okay.
So AI and ML models, they start with getting a data set from storage. And what we've seen is that a lot of the different nodes share the data, so we introduce caching to help with that. But when you have different models, they often share data as well. So when you were looking at the topology, did you consider that different models, while they'll be running different jobs, may be sharing the same basic data sets?
Good question. Good question. Short answer is no. And I think what you're suggesting opens room for maybe a topology for data sharing and maybe a different topology, like a shared topology for data sharing and a different topology for compute. I love that idea. Thanks.
So could we do an offline heavy-duty congestion control chat after this? I am a big proponent that flow queuing, which is slightly different from fair queuing, it's somewhat related to PF sense, if you're familiar with that, gives you a less pessimal outcome. You had some significant on-off patterns, and again, it'd be much better if we did this later offline and similar later.
Happy
Thank
to.
you.
Thank you. Of course.
Actually, I was wondering, is there like a mailing list or some discussion? Because I think there's a lot of people in this room that are going to be interested in all three topics.
Okay,
Is there a way we could have a conversation
my student
continue?
is here. Sudarshan, are you online? I'm going to get my student to set it up.
We can get you a mailing list in a few minutes.
My student is going to do this in a jiffy. I'll make sure this happens, Tom. Thank you.
Yeah, at one point we had something in Netdev. It really didn't fly. But that's also a lead-in for one of my questions. So the MLTCP, how far has that gotten? Do you have some precursor work, or is this just an idea?
My students should answer this question. We have results, and we have actually our algorithm is quite simple. It should be very easy. So we have stuff that work, but it's not published. So halfway done?
Okay, so no, that's the wrong person. Okay. That's the wrong person. It's Sudhir. And I know he's online, so you can bring him on. SU.
Sudarsanan.
Yeah.
He came up with the algorithm
SU.
2 weeks ago, and
D.
implemented it in 2 weeks. Cool. So
yeah, that's him.
halfway done.
Yep.
Oh yeah, here's Sudarsanan. He's really the brain behind the congestion control piece.
There's a question there too on the screen in the big font. The large question.
Oh, can you predict the computation communication time of every algorithm?
So while we wait for the online question, can I just slip quickly one?
Yes.
Yeah.
Yes.
So have you tried characterizing the error that comes from the multiplications?
It's Gaussian.
Gaussian, okay.
Okay, so there is a question on the screen.
Yes, I read it. So the question says, can you really predict this compute communication before even running the job? If you're thinking about isolation, yes, you can actually, another one of my students, his name is Frank. Frank has the mathematical formula to predict. The way to think about it is that you know the ML model. If you know how you're distributing the ML model, then it's relatively easy to think about the amount of data and the compute communication time. You do have to know the type of accelerator. You know, CPU versus GPU would be different compute time. You have to know the amount of, say, 100 gigabits per second versus 400 gigabits per second. But with some very easy sort of assumptions, you can actually predict. You can also profile. Like PyTorch and TensorFlow allow you to run one iteration, profile the whole model, and then you don't have to, run it until completion.
I think the point there is that if your job is going to run for 20 days or 30 days, it's worth taking half a day of profiling time.
Oh, much lower than, one and two iterations, yes. Or you can learn online. There's many, many ideas that if you can't predict, if your job is running for 2 days or 10 days, you can afford, a few hours to learn the traffic pattern. There's Sudarsanan. Sudarsanan, the question was, can you create a mailing list? And how far are you in your algorithm? Wait, we can't hear you.
We can't hear.
Hold on, hold on. Hold on.
I'm assuming you can hear us.
Can you hear us, Sudarsanan?
Yeah, I can
All right,
hear you.
great.
Now we
great.
can hear you.
Great, go ahead.
Oh, yeah. Oh, yeah, yeah. I'll create a mailing list and maybe share a link with you. Yeah, for the algorithm part, we have a rough idea on what properties the algorithm should have and also have a simpler version of it. Currently, we are testing it with TCQC and I believe like it could be made it to modify any other congestion control algorithms as well. Yeah, but we just started testing it. We don't have like full testing experiments, I guess, but yeah, it looks promising, the preliminary results.
So the question, I think, more is the implementation. It sounds like you have an overlay on top of the DCQC and implementation. Is that correct? Okay. So it's some overlay on top that can be applied to any other.
Well, is it just a new congestion control algorithm?
It's probably just a pacer, right?
No, it's just a parameter that we multiply the AIMD phase with, actually. And it's only DCQC, and right now we're very interested in doing this for TCP itself.
I think if a mailing list gets created, we would be very interested in seeing what the patch looks like, I guess is the next.
Yeah, definitely. Thanks, Sudarsanan.
Thank you.
Thank you. Any other questions? We are almost out of time. If not, thank you for a very spirited conversation. And
thanks, everybody.